So let's take a look at an example problem. And this problem here tells us that experimental tests using air as a working fluid are conducted on a portion of a turbine blade as shown in the sketch. So here's our sketch down here with the turbine blade. It tells us the heat flux to the blade at a particular point, x star, you see we have an x star that we're interested in here, on the surface is measured to be heat flux is equal to 95,000 watts per meter squared. So to maintain a steady state surface temperature given to us as 800 degrees Celsius, heat transferred to the blade is removed by circulating a coolant inside the blade. So we have a coolant channel down here in order to do that. Let's take a little bit closer look at our diagram here. So we can see there's our coolant channel. We have our surface temperature of 800 degrees C. We have our length here of L is equal to 40 millimeters. We have our heat flux of 95,000 watts per meter squared. We have our ambient temperature over here for air. So T sub infinity is equal to 1,150 degrees Celsius. Velocity is given to us as 160 meters per second. And these are our original conditions. So now that we've read through the problem statement, taken a look at the diagram, have a little bit of an idea of what's going on, let's figure out what they're asking us to solve for. So they're asking us to solve for two different things in this problem. The first thing they want us to do is to determine the heat flux to the blade at this position x star if the temperature is reduced now down to T sub S1 is equal to 700 degrees Celsius. And they're doing this by increasing the coolant flow. That's the first part of the problem they want us to solve for, is when we have this reduced temperature. Part two, they want us to determine the heat flux at the same dimensionless location, this x star again, for a similar turbine having a blade with a chord length of L is equal to 80 millimeters. So instead of L equals 40 millimeters, they want us to change that to L is equal to 80 millimeters. When the blade operates in airflow at the same T infinity is 1150 degrees Celsius, velocity is 80 meters per second, and our surface temperature is the same, 800 degrees Celsius. So two different things they need us to solve for. So now that we've had a chance to look through the problem statement and given schematic, we want to go through and write out exactly what they have in the problem statement that we know, what we're looking for, and what assumptions we're going to make. So we have two different cases here, because remember from the problem statement they asked us to solve for two different things. So one of the main differences there was a reduced surface temperature. So in case one, we're actually dealing with a surface temperature of 700 degrees Celsius. So for case one, surrounding ambient temperature of the air, 1,150 degrees Celsius. Velocity V1 given to us is 160 meters per second. Our L1, our length here is 40 millimeters, which we convert to meters right away of 0.04 meters. So that's that length over here, L. And our surface temperature, T sub S1, is 700 degrees Celsius. So we've redrawn out our diagram over here, slightly simplified, just in terms of general variables now, because they'll change from case 1 to case 2. So we have our heat flux at the surface, our surface temperature, our coolant channel, our length L, velocity and temperature of our surrounding ambient air. So now that we have our diagram there and we've looked at case 1, let's go ahead down to case 2. So case 2, a couple things will change. The overall length will double and the surface temperature will go back to our 800 C. So for case 2, our ambient temperature for air is 1,150 degrees Celsius. Velocity stays at, velocity is at 80 meters per second for V2. Our length here is 80 millimeters. We convert to meters is 0.08 meters. And our surface temperature here, TS2 for case 2. So you can see my indices 2, 2, and 2 for case 2 is at 800 degrees Celsius. So now what are they asking us to solve for? Well, for both of these cases, they want us to find the heat flux at this position x star. Assumptions we're going to make, well, in the problem statement it told us it was steady state. We're going to assume incompressible flow. We're also going to assume constant air properties. Now that we've gone through our problem statement, clearly defined what we're given in the problem statement. The two different things they're asking us to solve for, case 1 and case 2, have our initial diagram and our assumptions written down. Our next step is to go through our approach for our solution. And the key thing we want to do here is come up with our general governing equations. So for our case here, what we want to look at is Newton's law of cooling. So this will be our first governing equation here. So we have our heat flux is equal to H times T infinity minus Ts. We have our ambient temperature and our surface temperature here. We can rearrange this and solve for our H. We do this here, and H is equal to our heat flux divided by our temperature difference of T infinity minus T sub S, which is our air temperature and our surface temperature of our blade. So, from our known conditions given in the initial diagram, we can then solve for H. So we can plug in for these values up here. So we have our heat flux given to us, we have our temperature of the air, we have our surface temperature given to us for each of the cases. So we'll do this here. We'll plug this in for this case here. H is equal to our 95,000 watts per meters squared. Temperature difference here is 1,150 minus 800 degrees Celsius. We do this out here and we end up with, one thing we want to note is our units in the end are going to have a K in it. This has a C. You can do the conversion, but the difference of the two will be the same, whether it's C or K. We can do the conversion in the end. So if you notice, my units from unit analysis here is watts per meter squared times Kelvin. So this is still correct. H is equal to 271.43 watts per meter squared times Kelvin. Now, we assumed constant properties for air, so our L and our K do not change. So now that we have our H value here, we want to take a look at case 1. So for case 1, we want to go back and solve for our Q-1 or our heat flux for case 1. So we can go back to Newton's law of cooling, plug in our specific variables for this here, which is T sub S1 here. So our heat flux for case 1 is equal to our H value that we just solved for times this temperature difference here. So plug in our known values. Our heat flux for case 1 is equal to 271.43 watts per meter squared times Kelvin, right here, times our temperature difference. So our temperature difference is 1,150, again in degrees Celsius, minus our 700. So this is the difference here. But now we're dealing with our surface temperature that's reduced to 700 degrees Celsius. So you can plug that value in there. And again, difference in temperature, Celsius, Kelvin, doesn't really matter. If you're worried about this, convert to Kelvin and prove it to yourself as well. So we do that out. We get our numeric value here for our heat flux for case 1 is equal to 122,000 watts per meter squared. So now that we've solved for our heat flux for case 1, we want to go ahead and do the same thing for case 2. But the first thing we want to do is realize that there's going to be a difference between case 1 and case 2. So in case 2, the main difference is we have a larger blade, so the length increases, it doubles in length. So it goes from 40 millimeters to 80 millimeters and doubles. The airflow is reduced, so the velocity decreases by a factor of 2. So now, due to this fact, the Reynolds number is going to remain the same. It does not change because our length is doubling, but our velocity is decreasing by a factor of 2, which will keep our Reynolds number the same. And to prove that for ourselves, we have here for case 1, our Reynolds number here in this for this guy is equal to velocity 1, length 1, over our viscosity here. So we plug in our values here. Our velocity for case 1 is 160 meters per second. Our length is 40 millimeters or 0.04 meters, all over our viscosity V, which will remain the same. So this gives us a value for Reynolds number for this case of 6.4 over viscosity. Now, for case 2 here, we have V2, L2 over viscosity here, where V2 is now 80 meters per second, and our length doubles to 80 millimeters, or 0.08 meters. So 80 times 0.08 is the same as 160 times 0.04, which gives us 6.4. So our Reynolds number does remain the same for case 1 and case 2 due to the fact that our velocity is going to be changed by 2, a factor of 2, and our length is changing by a factor of 2 inversely. So it keeps these exactly the same for the Reynolds number. Now what will change is the convection coefficient. So in order to prove that this will change, what we want to do is take a look at equation 6.49 on page 401 of our textbook for our Nusselt number. So we have this general equation here. The Nu is equal to our H, our convection coefficient, times L over our K value there. And this is going to be a function of our position X star, our Reynolds number, and our PR number. And we can see we can define each of those by their equations, and none of these will change. But if we look down here for the Nusselt number for case 1 versus the Nusselt number for case 2, those are both going to be the same. But what's going to change in here is our L value changes from L1 for case 1 to L2. We know that that's given in the problem statement, but our K's are going to stay the same for this guy here. So if these guys stay the same and these change, that means our H's must change. So H2 cannot be equal to H or H1 in this case here. So now we're going to continue on with that equation there. So we can look for case 1 versus case 2. And what we want to do is rearrange this in order to solve for our H2. So this is what we want to look for in this problem here. So we can rearrange this solving for H2, and when we do that, H2 is equal to H times L over our L2 here, where we have numeric values for all of these. So H2 is equal to our H value here, which is 271.43 watts per meter squared times Kelvin. We solved for in the first part of the problem. And then we have our ratio of our lengths. So our length for case 1 divided by our length for case 2, where this is half of that. So this is 0.04 meters divided by 0.08 meters. We do this through, and it's basically dividing our H value for case 1 by 2. So 271.43 divided by 2 in the same units of watts per meter squared times Kelvin. We do this out and we get an H2 value here of 135.71 watts per meter squared times Kelvin. Now recall what they asked us to solve for on the problem statement is for our heat flux. So we still need to solve for our heat flux for case 2, where we now have our H value for case 2. So we can go back into our equation here that we've seen before for our H2 is equal to our heat flux divided by our temperature difference. We can rearrange this again and solve back again for our heat flux for case 2. So Q is equal to our H2 value here times our temperature difference. We have numeric values for all three of those. So we can say that our heat flux is now this H2 value that we just solved for of 135.71 watts per meter squared times Kelvin times our temperature difference in Kelvin here, which is now going to be 1150 minus 800 for case 2. We do this out, and what we end up with is our Kelvins cancel, so we're actually a heat flux in the correct units of 47,500 watts per meters squared. So now we've solved this for case 1 and for case 2 for our heat flux.